Hello and welcome. I'm Kamal Takodra. I'm a technical marketing engineer in the HPE Aruba Networking Switching Business Unit. And today I'm really pleased to bring you some updates on our new release software 10.14 1000 for Aruba CX. So let's get into it. AOS-CX 10.14 1000 release now introduces handling of overlay multicast using pin bidirectional multicast in the underlay for a single EVPN VXLAN fabric with IPv4 in the underlay. Now, overlay V4 and V6 multicast and L2 and L3 VNIs are supported. VTEPs, which form VSX, VSF or standalone, are also supported in this architecture. Aruba CX uses star homology shared trees using pin bidirectional to build the underlay multicast topologies, and no feature packs are required for this enhancement. Let's now step back and look at both head-end ingress replication and compare it with underlay replication. So first off, we look at head-end replication. We have multicast in the overlay. In this example, we have three multicast receivers sending a IGMP join. These are forwarded to the spine, and these are in turn forwarded to the multicast source VTEP on the far left. The multicast source VTEP for CX replicates the source traffic for each VTEP, as shown. This burdens the multicast source VTEP as well as increases traffic between the source VTEP and the spines. The multicast traffic is then forwarded by the spines to the multicast receivers. Now let's take a look at underlay replication. With underlay replication, we have multicast in the overlay, and we've enabled pin bidirectional in the underlay using the commands below. As before, the multicast receivers send a IGMP join. We also send a join in the underlay to the PIM RPs. We also have an IGMP join sent by the spines in the overlay to the multicast source. This in turn triggers the source VTEP to send an underlay multicast replication packet, and in turn the spines forward those to the interested receivers. We've reduced the multicast traffic between the source VTEP and the spines, as well as reduced the burden on the source VTEP. Overall, this lends itself to enable right-sized designs and improve capacity and scaling of single fabrics. The use cases here are overall layer 3 PIM sparse mode in the overlay. We have overlay layer 2 bridging of multicast, and really transitioning from a default mode of head-end ingress replication to underlay replication. So it's great for a customer who's moving from or upgrading a larger data center or large campus with EVPN VXLAN fabric, can move to this type of underlay replication. Overall, the customer benefits are a deterministic control of the multicast traffic in the fabric. We could improve scale and performance in the EVPN VXLAN fabric. Overall, it means there's a less burden on ingress VTEPs, and spine capacity and link efficiency are better utilized. The supported platforms are as shown. With the 6400, 8100 and 8360, as well as being an access leaf replication VTEP, they can also be spine aggregation and core, but in those personas they will be non-VTEPs and will be transit nodes. We also have the CX 8325, 9300 and the 10,000, which can be transit non-VTEPs in the spine aggregation and core. Now let's go over to a short demo. This demo topology, we are going to review EVPN VXLAN head-end ingress replication versus underlay replication when using multicast traffic in the overlay. In this topology, we have three VTEPs. VTEP 1, 192.168.1.20 on the CX6300, VTEP 2 at 192.168.1.159 on the other CX6300, and VTEP 3 at 192.168.160 on the VSX cluster. Each VTEP has a layer 2 VNI, 180 on VTEP 1, VTEP 2 and VTEP 3. We will use VNI 180 throughout this demo. VTEP 1 will be the source VTEP in all cases. We will be bridging layer 2 multicast in this demo, which is a typical use case. 4 multicast frames will be sent from a host on VTEP 1, and hosts on VTEP 2 and VTEP 3 will join multicast group 239.2.2.1. We will then compare ingress head-end versus underlay replication for multicast traffic. Now let's get to the demo. Let's start the packet capture. So that's started. Let's go across to our packet generator and send the 4 multicast frames. Now let's go back to our packet trace. Four multicast frames generated 8 frames at the source VTEP for stretch VNIs. That's 4 multicast frames times 2 VTEPs, which equals 8. So replication is proportional to the number of VTEPs across that stretched VNI. Taking a closer look at the first frame, we can see that the source of that frame is 192.168.120 VTEP 1 and the destination is 192.168.1.159, which is VTEP 2. If we look a bit further down, we will see that this is related to VNI 180 as we expected. And we can see it's a multicast frame. And we can see the destination multicast group 239.2.2.1. Now let's take a closer look at the second frame. Again, it's sourced at 168.1.20, which is VTEP 1. And we can see the destination is 192.168.1.160, which is VTEP 3. So this is the replication, first 2 frames of the first source multicast send that we sent from the traffic generator. And again, we can see this is related to VNI 180, and we can see that it's the source host of VTEP 1 host, which is here. And we can see that the destination is the multicast group 239.2.2.1. For each multicast frame sent, this is repeated per VTEP. We can see that on the third frame, we can see it's a source of .20 to .159, so that's VTEP 1 to VTEP 2. And then the fourth frame is VTEP 1 to VTEP 3. The cycle is repeated per multicast frame. Source VTEP frame replication increases with the number of VTEPs across the stretch VNI for multicast frames too. Now let's change to underlay replication. We see the default scopes selected by CX for the underlay multicast range. Aruba CX auto maps addressing and VNI 180 for layer 2 bridged multicasts, which we're going to demonstrate, is mapped to group 239.1.4.1 in the underlay for VNI 180. Now let's start the packet capture again. That's going. Let's go to our packet generator and let's send the 4 frames. Let's go back to the packet capture. Now we see that we've only produced 4 frames for each 4 multicasts we've sent. Let's have a look in a bit more detail. First thing we see, we have source of 192.168.1.20 to a destination which is a multicast address 239.1.4.1. So source 120, which is VTEP 1, and then the destination multicast address of 239.1.4.1, which was the auto generated and auto mapped address for the L2 VNI for bridged multicast. Back to the trace. And we can see this is related to VNI 180, and we can see that the packet is sourced from host ending 1082 with a destination which is the multicast group 239.2.2.1. That is the same for subsequent packets. Again, going to 239.1.4.1. This cycle is repeated per multicast frame, and frame replication is only sent once per source VTEP per VNI stretch. This method reduces the processing requirement on source VTEPs for multicast frames when we revert to underlay replication. And this helps reduce the burden on the source VTEP in these types of scenarios. I hope that was useful and informative for you, and thank you for watching.